Let's talk about something you might have had for breakfast this morning, your juice. Turns out there's a kind of invisible war going on right in that glass, a battle for safety, and it's being fought with one of nature's most powerful and surprising molecules.
I mean, it's a fair question, right? You grab a bottle of what you think is super healthy fresh juice, but what's really in there? Because even with the best processing in the world, there's always a chance something unwanted is hiding in there.
And by unwanted, we're talking about things like E. coli and salmonella. These invisible threats are a huge headache for the food industry. And, the traditional ways of dealing with them, they're not always perfect. In fact, sometimes the so-called cure can create its own set of problems. So for years and years, the champion disinfectant has been chlorine. And look, it works, but it's got a pretty big downside. It can leave behind some nasty chemical byproducts. But that's where our story gets interesting. It's opened the door for a new challenger to step into the ring, one that promises all that cleaning power, but with a much greener, cleaner profile. Okay, so who is this new challenger? It's something called ozone. And no, it's not some crazy chemical cooked up in a lab. It's actually oxygen's supercharged cousin, a close relative of the very air we're breathing right now. So what exactly is ozone? Well, think about the oxygen we breathe. That's O2. Two oxygen atoms, happy and stable together. Ozone is O3. It's got this extra third oxygen atom kind of tacked on, and it makes the whole molecule incredibly unstable, really twitchy. It's desperate to get rid of that extra atom and react with basically anything it bumps into. And that instability, that's the secret to its incredible power. So why should you care about this for your food? Well, for starters, ozone is about 1.5 times more powerful than chlorine. It's a beast against a whole spectrum of microbes. We're talking bacteria, viruses, you name it. But here's the absolute best part, the real game changer. After it's done all that heavy lifting, it just, poof, turns back into regular, harmless oxygen. No toxic residue, nothing. Which is exactly why the FDA has given it their generally recognized a safe stamp of approval for food. Okay, so we know it's powerful, but how does this supercharged oxygen actually destroy something like E. coli? The mechanism is actually pretty wild. It's not what you'd expect at all.
Yeah, it doesn't work like a poison. It's more like a straight-up physical assault, a cellular assassin. So instead of trying to poison the microbe from the inside out, ozone just goes straight for the jugular. It wages this brutal, direct attack on the cell's outer wall. It literally tears holes in the membrane, ripping it apart until the entire cell just disintegrates. And get this, because it's a physical attack, not a chemical one, microbes can't really build up a resistance to it. There's no defense against being torn to shreds.
And you don't have to take my word for it. You can see this process for yourself right here. This is incredible. In that first panel, you've got happy, healthy E. coli cells. But just watch what happens as they get exposed to ozone. In B and C, they start to warp, they get deformed, they're literally being ripped open. And by the time you get to that last panel, they're just gone. Nothing but cellular dust. It is total annihilation. Now, in the science world, there's a term for this kind of kill rate, a 5-log reduction. I know, it sounds super technical, but all it means is that 99.999% of the microbes are wiped out. And let me tell you, in the world of food safety, hitting a 5-log reduction is the absolute gold standard. It's how you know something is truly safe. Okay, so let's recap. We have a powerful, residue-free assassin that hits the gold standard of disinfection. It sounds perfect, right? Almost too good to be true. And, well, you know how it goes. With most things in science, there's always a catch. Which leads to the obvious question, doesn't it? If this stuff is so great, why isn't every single juice on the shelf treated with ozone? Well, the answer is that ozone is a bit of a diva. Its power is really, really dependent on the specific environment it's in.
A few things can really mess with how well it works. For one, temperature. Ozone works better when it's cold. Then there's pH. It's often more effective in acidic stuff, like a lot of juices. But here's the really big one, organic matter. You know all that pulp in your orange juice that you love? Well, that twitchy ozone molecule loves it too. It will attack that pulp just as happily as it attacks an E. coli cell. So the pulp and other bits in the juice basically act like bodyguards for the microbes, using up all the ozone before it can get to the real targets.
And this creates a huge dilemma for juice makers. It's a fundamental trade-off. Sure, you can blast that orange juice with enough ozone to get a 5-log reduction, but you might also destroy the vitamin C and wash out that beautiful orange color.
And you see the same problem with other juices too. You can kill the bad guys in strawberry juice, but you might also wipe out the healthy compounds that give it that gorgeous red color. So you're constantly walking this tightrope, a balancing act between safety and quality.
So, where does that leave us? What's the future for this powerful but kind of sensitive tool in our food supply? I think the main takeaway here is that ozone isn't a magic bullet. It's more like a scalpel. It's an incredible instrument that lets us disinfect food without leaving behind chemical junk, and that's a massive win. But to use it right, you have to be a surgeon. You have to understand the specific chemistry of every single food and dial in the perfect dose, the perfect temperature, the perfect timing, just to kill the bad guys without damaging any of the good stuff. And all of this leaves us with a pretty big question to chew on. As we get more and more powerful technologies like this, we have to start asking ourselves, what do we really want? What trade-offs are we, as consumers, willing to make? Would you accept a juice that's a little less vibrant in color if you knew it was 99.999% safe? It's a fascinating conversation, and it involves scientists, food companies, and in the end, it really involves all of us.